let's get into it. So yeah, this is just the overview, a little bit of background and motivation, the project. So we're in the setting of instruction following evaluation. So we want to take a post-trained model. So this is one that's had its SFT and RLHF process after pre-training. And we want to see how good it is at responding to a general set of instructions. And the two typical evaluation protocols here are preference and direct score. So either I'm given a pair of responses or more, and I want to rank them, or I just want to give all of them a score from 1 to 5, 1 to 10, whatever it is. And these all obscure any reasoning behind the evaluation by default. All I'm left with is a score or a ranking. And then, moreover, gathering these themselves are still expensive, despite the fact that you only end up with what's reduced to a single score. And this is where people start to apply LLM as judge. So now that we have very capable language models, it's natural to ask, well, are they comparable to humans when it comes to evaluating outputs? If they are in many tasks when it comes to generating outputs. And here there's some prior work on trying to improve instruction following evaluation by generating fixed data sets of instructions with specific checklists. So these checklists can be questions related to the instructions that ask, did the response meet this criteria of my instruction? Did it meet this criteria of my instruction? And this breaks down the instruction into a set of criteria that tell me where the model succeeded, where it failed, rather than just giving me an individual score. But the issue with doing this is that if you're going to generate a data set of prompts and then generate this checklist, that's a really expensive process as well. So you can do this for some fixed benchmarks, and it's great that they exist, these prompt checklist data sets. But it's not a general evaluation protocol that we can just apply out of the box to other domains. And then the second bit of background I'd like to go over is language critiques. These address some of the black box issues of standard evaluations by instead having a human evaluator or an LLM as judge provide natural language, a couple of sentences or more describing what was good about the response, what was bad about the response. And these can be used for as feedback to refine the response. So I can give this critique back to the model and say, can you improve your response based on this? Or it can be used to improve the performance of the judge or reward model itself. So similar to chain of thought, there's work showing that if you generate what is the equivalent of a chain of thought for an evaluator critique, then coming up with a final score, the model's better at this task. Or a reward model, if you condition it on the critique, is better at this task. And when I say better, I mean agrees more with humans. When we have humans that are trained annotators to evaluate a model, it agrees more. But then coming back to the point of improving the response in context, there's actually substantial evidence showing that this, which was assumed to be true, so there's 1 or 2 papers that claim massive improvements when I get the model to look at a critique and then improve its response. Yeah, so then like this table at the bottom here, which was just taken from another paper, shows that if you ask the model to correct itself, so identify mistakes it's made, and then correct itself on these range of common sense or maths reasoning data sets, then it actually gets worse over successive iterations. So self-correct round 1 is worse than standard prompting, and after another round, it's degraded even further. So they claim in this paper, and kind of my own investigations into this seem to imply that it's because they find errors that aren't there. So if you ask for self-correction, so you say find an error in your generation and improve it, then these models fail. If you give them an error in their generation, so if you say I've identified this issue, fix it, then the model's quite good at doing that. So it seems to be an issue with finding the errors more than it is correcting errors. Yeah. So yeah, given that background, I'll go into TIC, which is the LLM as judge evaluation protocol we came up with. So very simply, for a given instruction, we want to generate a checklist. So this is similar to what those benchmarks were doing that I mentioned earlier, except now we're not assuming that humans have written these for a given set of instructions. We're going to use the LLM itself to generate a checklist. For a pretty obvious case, this one on the right. We have this instruction: summarize the first season of the TV series Mr. Robot using a similar tone to the show's main character, Elliot Alderson. Use subheadings and bullet points for formatting and stay under 500 words. So naturally, the checklist can be: is the response a summary of the first season of the TV series? Is the response written in a tone similar to the show's main character? And so on. This is, yeah, for illustrative purposes, like a very obvious example. This instruction is one where you can very naturally decompose it into checklists. And we'll go through later what this looks like when that's not so much the case. Then we get the same LLM that generated the instruction to the checklist to individually answer each question. So it's not seeing all the questions at once. It sees the instruction, a response that was generated by whatever LLM we want to evaluate. And then it sees an individual question and it just has to answer yes or no. And then we can aggregate these into a score for the instruction by just seeing how many questions were answered yes and how many were answered no. Yeah, so this is just going through that. The main added thing is that we need a response of yes to correspond to a positive answer. This is because if we want to do this aggregation, we need to know what is good, what is bad. So when we request the checklist from the LLM, we request that all questions are phrased such that an answer of yes would be a good thing. So go back to the other one, it's all, was the response summary of the first season? For the word count one, is the response under 500 words? It would be wrong to ask, was the response over 500 words? Because then yes would be a negative thing. Yes, we answer each question in the checklist, and then we compute like a pass rate. So what percentage of questions were answered yes. This was a study we did to just look at how good the checklists themselves were. So we collected different sets of human written checklists from annotators. One gold standard set, which were kind of filtered and adjusted to be really high quality, and then two sets that were just what the annotators gave us. And this was to kind of capture the range of how humans would complete this task of checklist writing. And then we collected checklists from different LLMs, and we compared the checklists from different LLMs to the gold standard checklists and the other human checklists to the gold standard checklists. And we found that kind of some of the best LLMs already agree in terms of these various metrics more with the ground truth checklists than even some of the human written ones. So like Blue and Rouge are both string matching metrics. And we see higher numbers for like GPT-4o and Llama than for the alternative human checklists. And also in terms of question count, where humans actually varied quite a lot from the gold standard. So some humans wrote way fewer questions than we would have liked, some wrote way more. And then the next thing we want to validate is the answer quality. So here we also collected a bunch of human answers to the checklist questions for a set of responses that were generated by an LLM. And we took a majority vote among 3 annotators as the ground truth answer. So for a given checklist question, yes or no, as according to a majority of 3 human annotators. And then we just compute the accuracy for this binary classification task of different evaluator LLMs. And we find that it's reasonably high, but that it also scales if we assign more inference compute to the evaluator. So if we allow the evaluator to generate a chain of thought before it answers a checklist question, or we use a majority vote among more and more generations, then the question level accuracy increases. So this kind of indicates that similar to lots of stuff you'll have seen around inference scaling, this domain of evaluating also benefits from inference scaling, which is nice. And then kind of the main result for this protocol, before we go on to kind of what that then means for capabilities, is that it improves agreement with humans relative to kind of like what people typically do with an LLM as judge. So this WPLD, I won't go into too much detail about the metric itself, but it's basically just a classification metric for this where we have three different labels, win, loss, or tie. And it ranges from 0 to 2, with lower being better. So what we see is that preference is actually way worse than everything else, which is interesting because this is a preference task. So here we had a load of responses that we asked human annotators to give us, their pairwise preference for, as you typically do with LLM evaluation. I prefer this response to this response. And then we're trying to see how well the LLM as judges, according to the different protocols, agree with those human judgments. And if you ask the LLM for a preference in the same way you did humans, it's actually really miscalibrated. If you ask it for a score 1 to 5, and then you just take the highest score to be the preference, does better. If we do this thing that we call check then score, which is where we do the whole checklist generation and answering, but rather than use the answers themselves to form a score via the checklist pass rate, we just say, okay, given your answers to the checklist questions, given what that tells you about the response, come up with a score 1 to 5. So that's like some combination between scoring and checklist writing. And this does better again. But then if we do tick, which is generate the checklists, answer the checklist questions, and then just aggregate those by the checklist pass rate, the score that you get out of that, if you take the highest again to correspond to the preferred response out of 2, this agrees the most with the human preferences. So this kind of shows us that, one, the checklists are helpful for decomposing a instruction and a response into something that's easier to evaluate. And then 2, that just using those alone to form a score is more reliable than then giving those back to the model and say, okay, give me a score, because there you're introducing kind of more room for error and subjectivity into what the model gives you. So then in this next section, in context self-improvement with self-tick, SICK, yeah, I'll go through the method and then the results that we got and what that kind of means for where I think this could go next. So given an instruction, we now want to generate n responses and a checklist. So we're doing the generation and evaluator roles. And then given the instruction checklist response triplets, so instruction and checklist are fixed across all the responses, we want to answer each question in the checklist for each response. So n can be 1 here. It's probably easiest to just start thinking of instruction response checklist. And then I'll go into what we can do if we want to generate multiple responses. Then we can use these checklist answers that we generated from the checklists that the LLM has been given the instruction, it's generated the checklist, generated a response. For its response, it's answered the checklist questions. We can then give the checklists and the answers back to the LLM and say, try to improve your response, given what you concluded you got right. So, given the things that you said you got a yes to and the things that you said you got a no to. And you can iterate this process if you like. Or if we want to generate multiple responses, we can do a best of n selection according to our checklist pass rate. So we can filter, if we sample 8 responses with some temperature, then we can take the 1 or any that are tying for best according to the checklist pass rate that we gave ourselves as the generating LLM. And here are some results for 2 kind of general instruction following data sets, for stick versus self-refine, which is just if you ask the LLM to, so going back to what was done earlier in this table, where you just ask, critique yourself and improve your response. And here they showed that, on these maths problems, it got worse. In these general instruction following settings, so like not maths kind of problems where it's not really self-correction, but more of just, you want to improve your response in a more subjective way, self-refine still actually does give you positive improvement, kind of not as high as they indicate in that original paper, but we're kind of back in the regime of being able to improve. But stick gives you much sharper improvement. So we see up to like 7%, basically in both benchmarks. And now if we go to a different data set called Live Bench, which is a set of, I mean, as you can see, coding, data analysis, maths, reasoning, many of these problems are more like the ones where that previous paper that I mentioned showed that self-correction fails. We reproduce the result that self-refine leads to massive drops in performance. But Stick is actually able to, in these settings, still sustain improvements. So where self-refine, you're catching mistakes that weren't there, and you're decreasing the quality of your response. When we use Stick, in these settings, we're still able to improve, like Command R plus, reasoning plus 7.8%. So this is a pretty substantial jump. And I guess our hypothesis for why this works would be that first decomposing the task you were given into a checklist of things that your response should meet. So for a reasoning problem, was the chain of thought, the checklist would look like, was the chain of thought consistent? Was this part of the prompt correctly reflected in the response? Were all mathematical operations executed correctly? These kinds of things. Breaking the task you were given down into these yes/no questions and then answering them is a much easier task to get each of those questions right than to just look at a response and go, oh, I need to come up with a critique. I could kind of say anything based on what I just responded to the prompt. So my main kind of thinking about this method is that greater scaffolding and kind of structuring of how you use LLMs in these kind of agentic workflows where you prompt an LLM and then its output is being given back to itself, or prompting another LLM. It's really important to get the structure of that right, because you can otherwise get these compounding errors like self-refine. And the more highly you structure the task and the more you constrain the output space, the more reliably it seems to be able to do these things. So you've seen similar papers showing that getting an LLM to use JSON outputs massively improves performance, and these I think see that as a similar-ish result. And then so going to the best of n selection setting, where we're generating multiple responses and filtering, finding the best according to our self-evaluations, using the checklists. We again do better with Stick than if we use some reward model, Armo RM's like a really good open source reward model, or if we try to directly score our responses in that open-ended way we've discussed of, I'll just give it a 1 to 5 score, and try to select the best that way, is less reliable in terms of precision, and then that means it's also less reliable in terms of the score of the best selected response. And then just as a final thing that we tried with all of this work was to actually go back to human evaluation, which is still going to be an important way of seeing how good your LLM is. We're always going to have human evaluation kind of at the end of the pipeline. And saying, can we take the checklists that were written by the model, and can they help human evaluators in the same way they help the LLM as judge evaluator? So, similarly, providing these automatically generated checklists to a human evaluator might help them break down the task, make sure that things aren't missed, that they should be looking for in a response. And yeah, so for Wildbench, which is one of the instruction following datasets we were looking at earlier, we had GPT-4o generate a bunch of checklists for all of the instructions in that dataset. And then the annotators were given their usual task of providing a 1 to 5 score, but they could answer the checklist questions first. So this is slightly different to what we were doing with Tick and Stick, where we were using the checklist scores themselves. Wanted to keep the kind of standard annotation workflow, which was a 1 to 5 score, but say first just go through this checklist, answer the questions, and then use that to help you come to a score. And we found that this increased in an inter-annotator agreement significantly. So this is a measure of how much, if you have multiple annotators evaluate a single response, how much they agree. The higher agreement tends to be considered a good thing, because it means the annotators are kind of well calibrated on what they think a good response is. And yeah, we increased agreement without changing the average score very much, which implies that we were getting variance reduction without adding bias to the score. You know, if the score changed a lot and we got higher annotator agreement, then you could say like, oh, well, the checklists meant that all annotators were just giving higher or lower scores or something like this. But they seem to be kind of like just aggregating around the mean of their responses before, which is just means that there were less outliers, which generally like is an indication that an annotator slightly misunderstood the task or didn't get something. They missed something in the response or the prompt or one of these things. So that was a nice result. And then yeah, just what I think is some exciting future work based on this. Checklists are like only one heuristic for evaluation. So again, thinking of this as just a way of structuring the task of automatic evaluation better. There may be like many other ways of doing this. Checklist was kind of the first we tried and it worked well, but that kind of indicates to me that there's probably many other things we could find, like many other ways of doing this we could find. And maybe there's some way of finding these automatically. Can we improve further by actually fine-tuning on synthetic data that we filter by tick? So using this best event approach, as many people have done, you generate a load of solutions, you do best event with tick, you build a data set of those, and then you fine-tune. It would be cool to see if how that does compared to other approaches. And similarly to how reward models are often conditioned on natural language critiques, could we condition them on these checklists and see if that improves their agreement with human evaluations? Would be something else I'd be keen to try. I think that's everything I have. Yeah. So thanks very much for listening, and I'll take any questions.